Oh, he's not here. Do you want to see it? Anyone else want to see it? Yeah, that's funny. I don't know. Oh, in principal stresses? He's. Oh.
Yeah, and there's solutions online.
Okay. Okay.
It does take some work to figure out the rest of it.
Okay, let's skip that then. All right, so any other homework questions? Let's do one more internal loads problem. This one problem will be on the quiz.
Really?
No. Okay, so let's say we have a distributed load. The length of this beam is 0.5 meters. The distributed load has a maximum of 5,000 newtons per meter. And there's a torque of 800 Newton meters. And we want to calculate the internal load. Okay, so the first thing that we usually do is calculate the external loads. In this case, we can get away without doing it. So notice that if you ever have a beam that's a cantilever on the right side, you know, the things that happen all the way on the right never come up because we're working from the left. So our last cut is valid right up until that point. And so we can skip that step here. And in fact, I do that on tests pretty often to cut down on the amount of time a problem will take, you know. So pay attention to that. If you see a cantilever on the right, you can skip the step of doing the internal loads. Doing the external loads. On the left, you need to do it, or work from the right, but I don't recommend that. Okay, so we have to identify all the places where the subfunctions could change. That's the endpoints. Locations of point forces or point couples. There's none of those that aren't at the endpoints. And then any place where the function defining the distributed load changes. That doesn't change. That's the same function the whole way. Let's start by figuring out what this function is. Okay, so this is x equals 0, this is x equals 0.5. That function q that we're going to want later is the function that for any x value from 0 to 0.5 represents the height of that distributed load. Okay, so q of x is equal to the slope of that line. The slope is the rise, which is, you know, it ends at 0, starts at 5,000, divided by the run, which is 0.5. All that times x, that's the slope times x, plus the y-intercept. The y-intercept of that line, when x is equal to 0, y is 5,000, so this is just plus 5,000. So the distributed load function is negative 10,000 x plus 5,000. And now we can do our one cut. This is valid for any x value between 0 and 0.5. Okay, so I'm going to stop drawing that light blue part, but there's a whole part of the beam that's cut off over here, and we're ignoring that. We're only isolating some piece on the left. And so the loads, you know what? No, I am going to draw it. Okay. So over here, there's the torque. That was 800. And then there's the distributed load. And notice that that distributed load doesn't come all the way down to a point. Okay, so the part that we're chopping off means that instead of this being a triangle, it's a trapezoid. It ends up being a real pain in the butt. The good news is we do know what the value is over here. That's 5,000 at the highest point. And then we have the internal loads, tension, shear force, bending moment, torque. So now that we've chosen a piece to isolate, and you know this distance is x. Now that we've chosen a piece to isolate, we can represent this distributed load as a point force, okay? Because we've already specified what piece we're isolating. So that means that we have to figure out the area of this trapezoid, and we also have to figure out the centroid. So here's the trapezoid.
So we're gonna break it up into two.
That's what I'm going to do, yeah. I think that's the easiest way. So,
I know, but to find that, wouldn't it be easier to work with two triangles in the center?
I've never thought about doing it that way. It would work, yeah. You could do it that way. Well, here's the way I'm going to do it. Because, I'll think about that. Yeah, that would totally work. Maybe that would be easier. Anyways, I'm going to do it as a triangle sitting on top of a rectangle. We know that this length is x. We know that this whole thing is 5,000. And what's the height at this corner? So remember that this side is represented by the value x. So how do we know what the height is there? If only we had a function. Yeah, right, that's q. So this length is 10,000x minus 5,000. That means that this height is also 10,000x minus 5,000 because that's a rectangle. And so what we really need to break this up into a triangle and a rectangle is we have the 5,000, but we really want this height of the triangle. So we can do that as just 5,000 minus this. That's going to be the height of the triangle. So 5,000 minus the quantity 10,000x minus 5,000. The 5,000s cancel out. Do they? Yes. No. 5,000, because this should be plus. That's why they cancel out. So 5,000 minus this quantity gives you a value for this triangle.
That should be negative 10,000.
Yes. Thank you. So this should, the height of this triangle is negative, positive 10,000x. Okay, so the area of the triangle is 10,000x times x divided by 2, so 5,000x squared. And what's the x value of the centroid of the triangle? Yep, good, 1/3 x. Yep, and b is x in this case. See that? So x over 3. And then for the rectangle, the area of the rectangle is x times the height. So that's negative 10,000 x squared plus 5,000 x. And the centroid of the rectangle is just the middle, so x over 2. If we wanted, we could figure out what the total area is by adding up this area with this area, and then use the centroid sum formula to combine these to get the centroid of the whole thing. But that doesn't help at all. So what we're going to do is just keep that as two individual shapes, each one producing its own point force from its own centroid. Okay. So now I'm going to draw a new free body diagram. We have the torque and the internal loads. And then from the distributed load, we have a point force at the center with a magnitude of negative 10,000 x squared plus 5,000. And then a third of the way from the left, I'll just put it down here for neatness, with a magnitude of 5,000 x squared. Okay, so this sort of looks like it might be a negative value, but notice that this is only valid for x's from 0 to 0.5. And so as long as you're between 0 and 0.5, this is positive. That should be 5,000x, right? Yes. Any questions about that? Okay. The location of those centroids are each going to come up when we calculate the moments produced by those forces. But so it's important to notice that this is positive, because that means that it is going to be a downward force, and that means that the moment is going to be whatever that is clockwise. Okay.
So the bending moment on the right side of that free body diagram is going counterclockwise or clockwise?
It's positive if it's counterclockwise, and we'll see what it is.
So when we said it's clockwise, that is referring to the midpoint between there and the right side? Or
that's saying a downward force acting over here to the right of the about point would make this beam rotate clockwise. Okay. And so this is going to produce a clockwise moment. Okay, so Newton's second law says 0, negative 5,000 x squared plus 0, and now, okay, so this can easily confuse you. But this is a positive value, right? And it's acting in the negative y direction. I think the easiest way to think about that is you have a magnitude and a unit vector that you're multiplying together. The unit vector is 0, negative 1. The magnitude is this thing. So now we're going to have a y component that's the opposite of this. That's what happens when you multiply that value by that unit vector. So that gives us a y component of positive 10,000 x squared minus 5,000 x and plus t minus v is equal to 0. So tension is 0 and shear force is positive 10,000 x squared minus 5,000 x squared. So positive 5,000 x squared minus 5,000 x. And then the moment equation about the x-axis. All we have are this couple of 800 Newton meters, and then the torque, the internal torque. So that's negative 800 plus fancy t is equal to 0. So the internal torque is positive 800. And then the moment equation about the z-axis. All right, so what's going to produce moments about the z-axis? This won't. That's about the x-axis. This will. This will. Then the couple, and then v. Okay, so first, the 5,000 x squared. What's the moment arm for that? Yes. So the moment arm is x over 3, and that force would produce a clockwise moment, so it's negative. So we have negative x over 3 times 5,000 x squared. The magnitude's 5,000 x squared, and that'd be positive inside this range. And then what's the moment arm for this next downward force? Yeah, that's x over 2. That would also produce a clockwise moment. So that's minus x over 2 times that ugly expression, negative 10,000 x squared plus 5,000 x. And then the moment m. And then what's the moment arm for v? Yep, and that's how that always shows up. And that would be a clockwise rotation, so that's minus vx is equal to 0. All right, so m is equal to, we have positive vx plus 1 666.6 repeating x cubed. That's plus. And then this would be minus 5,000 x cubed. And then plus 2,500 x squared. Everyone agree with that? Okay, and so the last thing we have to do is plug in our expression for V. So the bending moment is equal to 5,000 x cubed minus 5,000 x squared plus 1666.6 repeating x cubed minus 5,000 x cubed plus 2,500 x squared. And now we can lump all this stuff together. So m is equal to, so we have the 5,000 x cubes cancel out, and we just have 1666.6 repeating x cubed. And then the squares, whoops, that's an x squared. Minus 5,000 x squared plus 2,500 x squared, so that's minus 2,500 x squared. And I think that's everything. Okay. Okay. Okay, so if this is our function, so now we can do that derivative check that catches a lot of mistakes you make, because there's a lot of stuff where it's pretty easy to make little mistakes with a negative sign or whatever. So now we have all the functions. Let's check it out. So the first one, dm dx, is equal to positive 5,000 x squared minus 5,000. And then compare that to v. Dm dx has to be equal to v, and that works out. So that one's good. Yes. And then the second one, dv dx, is 10,000x minus 5,000. And we're comparing that to the negative of that distributed load function. So way up here, our q is negative 10,000x plus 5,000. That one works. And then all the endpoint stuff, yeah, I can see that stuff works too. Pretty obvious.
Oh, yeah.
Yeah.
Works. Are you going to quiz us on 3 to 5? Or put it on an exam?
That'd be a good thing to put on a quiz. No, on exams, you never have to do the checks, but it's a good way to catch your errors, you know. Any questions about any of that? Okay, so now that we know how to calculate the internal loads, we're going to use those to calculate the stresses in beams. So we'll use the internal loads to calculate the stresses in beams. And so to do that, we have to know how to calculate the stresses that come from tension, bending moment, shear force, and torque, okay? Each one of those types of internal loads is responsible for its own contribution to the stresses. The total stress tensor then is going to be equal to the stress due to tension plus the stress due to shear force plus the stress due to bending moment plus the stress due to torque. For example, if you had a stress due to tension that was equal to 5, 0, 0, all the rest zeros, plus a stress due to shear force that was 0, -2, 0, -2, 0, 0, all the rest zeros, plus a stress due to bending moment that was -10, all the rest zeros, plus a stress due to torque that was, say, 0, -6, 0, -6, all the rest zeros. That would give you a total stress tensor of -5, -8, 0, -8, and all the rest zeros. So you just add it up element by element. This is called the superposition principle. And this idea of superposition comes up in a lot of engineering applications. The idea is that the actual state is what you get by treating each individual component of that state independently. So the actual state is the same as if did component states independently and then added the results up. Almost always, the superposition principle requires small values in some way. It's not like generally the case. It's actually never exactly true that you could, like, imagine this beam. You're looking at the stresses at a single point, and if you're twisting it and bending it and compressing it and all this other stuff, it doesn't seem very likely that the total stress would be the total stress that would occur by calculating those independent loading, states and then adding the results together. The reason that it more or less pretty close to works, the reason that it's useful, in our case, comes from two facts. or let's say two assumptions. And this has to do with those four assumptions that we're making in pretty much every problem in this class. The two that matter here are linear relationship between stress and strain, and small deformations. Okay, so if you think of a material that wouldn't have a linear stress-strain relationship or wouldn't have small deformations, like for example, a beam made out of rubber, you wouldn't have to apply a very big load to it for it to get relatively big deformations. And rubber never has a linear relationship between stress and strain. So if you did this calculation for this beam made out of rubber and you calculated each of those independent individual states of stress, the individual stress tensors, and added them up, you get a very different answer than the actual stress that's occurring. Okay, but in steel and concrete, for small loads in the elastic range, in the linear range, it works pretty well. Okay. So we just need to figure out how to calculate the stresses due to these independent individual things. First, due to tension compression, then shear force, bending moment, and torque. And I'm not going to do it in that order. So great. How do you calculate the stresses due to tension compression, bending moment, shear force, and torque? Well, we don't know how to do any of these yet, but that's what we're going to spend the next few weeks on. So one by one, we're going to go through these. Tension compression, we've actually sort of dealt with that already. So that's the one we're going to start with, because we've already dealt with stresses of objects that are loaded like a stress element. And one of those things was uniaxial tension or compression. And so that's the same way it works here. Great. How do you calculate the stress due to these four things? It's a long question. Well, I'll tell you. Yes. Okay. Any questions about that? I guess we'll start with that on Wednesday. Let's take the quiz.